All right. I think I'm recording now. Yeah, I am. So so let's see, guys. I see a lot of nice work here. Some people have made 2, some people have made 3 drinks, some people have made I think that if I remember right, someone made a 1/3 of a drink. That was Hong's, right? Yeah. All right. What if I was to make like square root of 2 drinks? 1 drinks because your parents don't want to drink it? Dude, but it's gonna be really tasty. Why wouldn't they want it? Hong, you made 1/3 of a drink though, when with yours, because you divided everything by 3. Or wait, was that Hong's? Someone had done that. Someone had divided it all by 3. Yeah, it was Hong. Yeah, he's only 1/3 human. He's built different. He only wanted a taste. Dang. 3 handful of ice. I feel like what is 3 handfuls of ice? Like what do you guys think is like a appropriate amount of measurement? Like 3 handfuls of ice, I feel like that's maybe like 1.5 cups. Like 1 handful of ice, that feels like a half cup. 5 to 10 cubes. Dang, that's a lot of ice cubes to be putting in your drinks, guys. You're gonna water down all your drinks. Y'all the type of people to get 100% ice in your boba, huh? You guys are missing out. Think about how much more liquid you could have if you didn't have all of that volume. Okay, and be hydrated. uh, I got 0% ice one time when I got the if you ever get like the brown sugar milk, you know what I'm talking about. I got like 0% ice at that one time, and it was like a huge mistake. It was like a huge mistake because it it wasn't cold. It was like kind of warm. I feel like it didn't work as well. I don't know if it's just me, but you're kind of quiet. I'll try to bring the mic closer to my mouth. I think I'm gonna try to not talk too loud, just because I'm a respectable adult. All right, y'all. Let's move on. So guys, here's what's up. Here's our agenda for today. So we are going over last week's topics a little bit. We're going to talk some connections between what we call the unit circle. This is an idea you guys might have heard of, you guys might be familiar with, and trigonometric modeling. And we are going to today be building the unit circle. We're going to be developing it as individuals. So, oh, I forgot that I put TBD on that. Dang, I should have fixed that. Oh well. So who can read the lesson outcome for us, y'all? Let's see. Who's going to be the one to read it for us? We have 30 participants in here. That makes 29 students. Let's actually here, I'll include myself in the.
All right.
Oh yeah, Nelly, go ahead. Tell us.
Today I will reinforce my understanding of last week's context, learn more. And why did you say something? Now you blocked the thingy. I learned more about connections between the unit circle and trigonometry modeling, and apply the special triangles to construct the unit circle. I'm sorry, my Zoom thingy like lifted
I
up.
I know what you're talking about. That's funny. Every time someone says something in the chat, it like pops up and was blocking it. That's funny. Yeah, I was about to do RNG, Christine. Thank you very much, Nelly. So yeah, so today is all about unit circle, guys. This is our big unit circle day, which is really not that intimidating, actually. It's kind of, we've done all the hard work, actually. That you'll see when we get there. All right, so guys, so to start things off, we are gonna be actually, oh, let me pull up this Desmos thing. So I want to actually give you guys the link to come back to our classwork that we had done last time. the problem set. And I want you guys to look at slide 6. So so can everyone please, you see in the chat, I've posted the link to our previous problem set. Please go ahead and go to that, open that up. And what we're gonna do is we're gonna have your classmate Jason showing us his solution and explaining it to us a little bit, y'all. So is Jason here? Yeah, he is. So I want everyone, please be clicking the link there to join us so you can see your own answers. And we're gonna have Jason tell us a little bit about how he got it. Hold up, I gotta plug in my mic. That's okay, because that gives people time to click the link. To finish my thought, yeah. Take a while, Jason. If he takes too long, we'll just have class go into past 11:50. Hong says I struggle with drawing on Desmos. What do you mean? You just say, you just draw it. You see that? Can't get the math sensitivity right. That sounds like a you problem. Yeah, I agree with Lydia. She's calling you guys noobs. I hear you, Lori. Jason, are you back, bro? Where are you? What happened to him? Yeah, I told him I had.
Yes.
Oh, there he is.
I'm
There he is. Look at it. Okay, we got our God King. All right, Jason, tell us a little bit about this. Can you please tell us, first of all, the 45, 45, 90, try. Oh wait, no, this was the first one that we did. Can you do the 30, 60, 90 first? Tell us a little bit about it. What did you do?
So the short leg, I know like the rule for the 30, 60, 90 triangle is that is the hypotenuse is like 2x.
Mhm.
And then the short leg is half of that. So I just got half of the hypotenuse for the short leg. That's why I got 2.
Nice.
Then for the long leg, it was like square root 3 of x for this. So I times x, which was 2, with square root 3, and I got 2 square root 3.
Excellent. Are y'all following him, or are you guys too busy talking about Demon Slayer in the chat? Busy? Stop being busy. All right, thank you very much, Jason, for that. So, so guys, in this problem set, I was checking, by the way, I was checking people's answers to this one on the problem set assignment and kind of giving people feedback a little bit. If you didn't do this part, then I think that I gave like 4 or 3 out of 5 and then asked you to do it. So if you just resubmit it, then you should be able to get credit back. Okay, and then what about this one here? Jason, I think that you had, oh wait, not 3. So what did you have, sir, for this one? He had 6 root 2 over 2. How did this come about?
For this one, I used ratios.
Mhm.
Since I knew the hypotenuse was square root 2, and it was 6, so I just did 6 over square root 2 times square root 2 over square root 2, and I got, since that doesn't change anything, I just got 6 square root 2 over 2 for for the
Yeah.
ratio.
So so in this, guys, he realizes that the ratio between the leg, right, and the hypotenuse in a 45, 45, 90 is supposed to be 1 to square root 2, right? So he said, if it's supposed to be 1 to square root 2, but I instead had 6 here, right? Then he needs to turn his 6. He needs to turn his square root 2 into 6. So he's essentially he's going to divide both sides by the square root of 2 and multiply it by 6, right? Do you see that? So the square root 2's cancel here, and he's left with 6 for his hypotenuse, which matches the triangle that we have. And then in the end, he gets 6 divided by the square root 2, which he rationalized by multiplying the top and bottom by that square root, right? Because remember, we want to try to get rid of the square root from the denominator, right? And in the end, he has 6 square root 2 over 2. Cool. Yeah, Millie.
Can you just 6 minus square root of 2?
Could you do 6 minus square root 2?
No minus.
Divided by.
Divided by.
Yeah, that's essentially what he was doing actually. So yeah, exactly. You could recognize that, and that's essentially what I was trying to explain actually in this proportions thing. Millie here is recognizing, guys, that in order to go from her hypotenuse to her leg, it's simply a matter of dividing by square root 2 because of this proportion, right? The hypotenuse is square root 2 times the leg. So essentially, if the leg is like x, and she's recognizing that like that 6 there is equal to the square root 2 times x, right? Here, let me erase some stuff. So she's recognizing that essentially the hypotenuse is always equal to square root 2 times the leg, x being the leg. So then she divided both sides by square root 2. This is exactly what Jason was saying he was doing actually. I kind of was showing what he said in a different way. So then x is 6 divided square root 2, which once again we rationalize. Any questions about that part, y'all?
Yeah. Is the 6 times square root of 2 over 2 is right answer? Because shouldn't it be 6 times square root of 2, then it's square root of 12? Then it's 2 over square root of 3?
I'm gonna actually, let me pull up my whiteboard. This will be a lot easier to draw on for us, for what you're saying. So Millie, if I hear you correctly, you're saying that, and I'm gonna switch my screen share, y'all. So please let me know that you guys can see it. Can y'all see that? Oh, what's up, Victoria? I see you. So Millie, you said you took 6 square root 2, and that is equal to the square root of 12. Oh, but it was over 2. Is that what you're saying?
Yeah.
Okay, so that's an interesting question. That's like, is this true, right? That's the question. So imagine, let's try, you know what we can do with this to test if it's true? We could think about what is the square root of 2? What is the square root of 12? And I think this is actually, this is a valuable thing for us to think about, because I think that it's kind of like, this is the kind of skills that we don't really teach often in math, but it's kind of like just the skill of estimation. So guys, the square root of 2, the square root of 2 is, I just want to point out something. Square root of 2 would be greater than the square root of 1, right? Can you guys agree with me on that?
Mm-hmm.
And it'd be less than the square root of 4, yeah?
Mm-hmm.
Well, the square root of 1 is 1, square root of 4 is 2. So therefore, the square root of 2, we know, is somewhere between 1 and 2, yeah? Does that make sense to people?
Yeah.
Okay, let's look at square root of 12 now. The square root of 12 would be bigger than the square root of 9, right? And it would be less than the square root of 16. The square root of 9 is 3. The square root of 16 is 4, right? So we know that 12, the square root of 12 is something like 3 point dot dot dot. We know this guy's 1 point dot dot dot, right? Does that make sense to people?
Yeah.
So looking at this, 6 times 1 point something, right? That's gonna still be kind of like 6, right?
Mm-hmm.
It's gonna be like it's gonna be a little bit bigger than 6, in fact. So what I recognize is that 6 squared can. By the way, guys, so I recognize that 6 square root 2 is something that's gonna be a little bit bigger than 6, and then divided by 2 would be a little bit bigger than 3, right? It's like somewhere that's a little bit, just like around a little bit bigger than 3. Oops. Okay, well, let's look at square root 12 over 2. We just showed that the square root of 12 was something around in the 3 range. Divided by 2 would be actually somewhere that's like kind of less than 3. Do you see what I'm saying? Because if I had 3 point some decimal and I divide it by 2, I'm going to get a value that's less than 3, right? Does that make sense to people?
Mm-hmm.
So what I've just shown is I haven't actually done any hard math. Like by hard math, I mean like calculating actual decimals and such. I'm just using kind of a little bit of logic and kind of my idea of like knowing approximations to show that these aren't equal. Okay. And the reason why this is not true, why I can't do this, is because actually of the way that we simplify square roots. If I have the square root of 12, that's going to be equivalent to square root of 3 times 4, right? 4 is a perfect square, right? So I could actually pull that out of my square root and call that 2 square root 3. So the square root of 12 is actually equal to 2 square root 3. Y'all see this? If I wanted to go backwards and put this 6 inside here, 6 square root 2 would equal, to put 6 back into the square root, I would have to square it. The square of 6 is 36 times 2. So actually, when I put 6 inside of that square root with the square root 2, I get the square root of 72. Do you see that?
Actually, I'm not asking on the thing. I'm asking if you both times 6, and it should be just up there, like 6 times square root of 2, then it's 6 square root of 2.
You're asking if we should simplify this.
Yeah.
Okay, yeah, that's a fair point. So in this can be simplified actually, guys, but not using the square root 2. Really, we could just recognize that what's 6 divided 2? Someone in the chat, it's 3. Thank you, Nelly. So actually, this thing is equal to 3 square root 2. That's what we would simplify it to.
So like if the whole number times one number with square root, then it's just gonna the whole number in front and the real number.
Exactly. Yeah, exactly. So whenever you guys are working with square roots and you're trying to simplify terms, we actually try to pull, you try to pull as much out of the square root as possible. And then anything which you cannot, like this square root 2 that we have here, you go ahead and just leave it. It is a factor of the term. It's a factor of my solution. Christine asked me to post this whiteboard later. Sure, if you want it. Here. You know, I'm gonna just right now, I'll post it onto our class Discord. I know not everyone uses that, but I feel like you guys can pull that up on your own, on your phone or something if you want to. It's in the math discussion. Okay, cool. All right, so I'm gonna go ahead and put us back to the problem that we were looking at. Do you not divide the square root of 2 by 2? That's a good question, Christine. I'm gonna put that over here. So Christine's saying I have 6 square root 2 over 2, and I want to divide by 2, right? the 2 only has to divide one of these factors, because what this is one whole term, right? Similarly, guys, if I had, for example, 6 times 4 over 2, what's that equal? It doesn't equal 3 times 2, which is 6, right? The 2 only divides one of them because they're factors. You see what I mean? So the
Yeah.
2 is not dividing the 6 and the square root 2, because the 6 and the square root 2 are actually one thing. They're combined. They are one number. A lot of people, I think, are just not very familiar with square roots because we haven't worked with them a ton in our math classes in the past. But what you guys will see, hopefully, over time is that really square roots are actually, they end up attached to the number and create like, what's happening is that it's just like when I have the number 12, actually. 12 is in reality 3 times 4, right? It has factors to it. It's just that when we have square roots, we show those factors rather than multiplying them together and getting a decimal. Because when I look at the decimal version of 6 square root 2, you start losing a lot of the context of like where this number even came from. Like if for example, Jason in his final answer, instead of writing it as 6 square root 2 over 2, had just written it as a decimal, I would know nothing from it. Like I would see it and I'd be like, all right, cool, there's the answer, right? But I wouldn't have gained really any insight into where this answer came from. And we wouldn't have even had this conversation about these things. Which I feel like conversations like this are some of the best things we can do in our math classes. Millie, you still have your hand up. Is that from before, or do you have a question?
Yeah, I have a new question. So
Yeah.
it's like, if one number is square root of something, then you times square root of something, then you're gonna times the number inside of the square root, right?
So if I had square root of 3 times the square root of 4,
then it's gonna be square root of 12.
That would be square root of 12, yes.
Oh, I see now.
This is actually an application of the laws of exponents. Do you guys remember those from before? The laws of exponents? If I had saying like, x squared times x to the third, that's x to the fifth, right? You add the exponents, or sorry, that's not what I meant. It was like if I have a squared times b squared, that would be equivalent to like ab squared, right? That's the one that it was. That distribution, it's actually a similar vibe here. This here is 3 to the power of 1/2, right? Because remember, square roots are fraction powers, times 4 to the power of 1/2, which is equal to 3 times 4 is 12 to the 1/2. It's the same law actually that lets us do this. Okay. I think that's been a lot about that kind of side tangent. So I'm going to go ahead and bring us back into what we were doing today. So can I have everyone please go to slide 7 on the on that Desmos activity, y'all. Yeah, I hope that was interesting. If it wasn't, and you tuned out, tune back in now because we're going back into our normal class stuff. Okay, so guys, in our mastery assessment that we did this weekend, what you guys were doing was actually solving for, you guys were using the special triangles, the 30, 60, 90 and the 45, 45, 90 triangle in order to solve for some coordinates along the perimeter of a circle. Now, it wasn't actually random that I had you guys finding those coordinates. I'm going to go to slide 8, by the way, y'all. This is kind of like a little bit of a representation of what you guys did in your mastery assessment. And you were filling in the coordinates here, right? what this is, guys, this is actually the first quadrant of what we call the unit circle. Now, I'm going to talk to y'all a lot more about the unit circle today and what it is and why we care about it. But first, I just wanted to quickly go over the kind of solution to this mastery assessment problem. All right, y'all. So you guys can go ahead and follow along on my live stream because I kind of want to save us some time. I was going to ask people to solve it for us or share their answers, but I think I'm just going to explain it to y'all today for now. So so first of all, in this problem here, y'all, we have a circle with a radius of 1, right? The radius is 1. So for example, at this angle of 0 degrees where it goes just directly to the right, that is going to be at 1, 0, right? That's going to be at 1, 0 because it's gone 1 unit to the right. Similarly, for 90 degrees, it's vertical. So it's gone 1 unit up. So it would be at 0, 1. These were like the kind of the odd ones because they didn't use the triangles, but they were ones that I thought I expected people could, through kind of just their own existing math knowledge and kind of observation and a little bit of critical thinking, I figured you guys could get those coordinates, right? And then here in these 30, 45, 60 is where we have the triangles, right? You can see here that this is actually a 30, 60, 90 triangle, right? Here's 30 degrees. Here's 60 degrees, right? And so following what Jason had helped us out with and what we were knowing about these 30, 60, 90 triangles, if the hypotenuse is 1 here, then the long side is square root 3 over 2, and the short side is 1/2. You see that? A lot of people saw this and were able to fill it in instantly, which is good. So the long side, which is on my x coordinate, right, was, we said, square root of 3 over 2. And the short side, which is my y coordinate, was 1/2. Does that make sense to people?
Yeah.
So I think that actually, yeah. So if at any point, y'all, you want to have me explain something further, just say in the chat. Just let me know in the chat because it's like you're not interrupting me with that. So don't worry about like like you don't need to worry about like, oh no, like is this like, you know, wait for a pause, right? You guys can always at any point in time just say in the chat like, okay, Mr. Hoba, tell me more about this thing. Here at the 60 degree one, I'm going to do just because we were literally talking about 30, 60, 90 triangle. So here I have a 60 degree angle and a 30 degree angle. So the short side is now my x coordinate. Really what's going to happen is these coordinates are just flipping here. The short side is 1/2. The long side, which is my y, is root 3 over 2. Now, the one that was actually a little bit challenging was the 45 degree because in it, our hypotenuse is still 1, right? And so then that's kind of requiring us to do the whole dividing by a square root guy. Luckily, however, if you guys had done this problem previously, right, I actually could just take all of the solutions that we had here and divide them by 6 and easily get that value without having to think too hard. But I won't do that. We'll instead, what I'm going to do is I'm going to draw the triangle here kind of small. So I have my 45, 45, 90. The hypotenuse is 1. So normally it's actually square root 2, right? And these are 1 and 1. So to turn it into 1, I'm just going to divide everything by square root of 2. You see that? Because square root 2 divides square root 2 cancels out and makes 1. And then 1 over square root of 2, we have to rationalize our denominator, right? So you would multiply square root 2 on top and bottom. And you end up getting root 2 over 2. Root 2 over 2. And this is our entire first quadrant of the unit circle. Do you have any questions about that solution?
No.
Cool. All right, y'all. Then I think we're good here on this part. And so now we'll get back into the kind of like presentation slide side of things. So you guys go ahead and switch your focus back. If you weren't already, switch your focus to this, to my like shared screen, please. And I want to talk to y'all a bit about the unit circle. Okay. So first of all, let's introduce what is the unit circle. So the unit circle is essentially, guys, it's like this basic tool that we use for kind of all trigonometry knowledge. It's actually even more useful than SOHCAHTOA since essentially it contains SOHCAHTOA within it. If you guys don't know what I'm saying when I say SOHCAHTOA, that is a thing from geometry which you may or may not have learned. And it's called the unit circle, right? So you can see here, the idea of the unit circle is just a circle that has been placed on the Cartesian plane. The Cartesian plane is like the XY axis and has a radius of 1. All right. Oops. I like to think of the unit circle as like the multiplication table for trigonometry, right? So essentially, guys, gaining understanding and fluency of the unit circle, I think it's like kind of similar. It's akin to knowing your times tables for algebra, right? If you don't know your times tables in algebra, like you don't know like the basic multiplication tables, you can do algebra. I see people do it all the time. I teach algebra, right? I see people all the time doing algebra without knowing how to multiply. But you're gonna have a really hard time doing algebra without knowing your times tables, because on the most basic end, every time you have to do multiplication and you have to pull out a calculator to do it, right? That slows you down, and it means that your focus kind of gets shifted, and it'll just make doing algebra harder because it's hard to kind of think about like a complex problem if every single step of the way is a new challenge. You know what I mean? If even like the multiplication is a challenge, then you're definitely gonna have trouble with the rest of it. Similarly, the unit circle is sort of like a tool that we will use to evaluate trig functions. Yeah, like I could use a calculator to evaluate sine of 30 degrees, right? But I'm going to have a lot of trouble understanding why sine of 30 degrees is 1/2 without knowing the unit circle. And therefore, I'm going to have a lot of trouble with applications because I'm not going to really understand what sine even means in the context if I don't know the unit circle. Okay. So it's a pretty important tool for us in trigonometry. So I wanted to introduce a little bit about it more. So first of all, the unit circle represents a circle with radius 1 unit centered on a Cartesian plane. Cartesian plane, by the way, guys, is the XY axis. This is that picture we had before, right? As the radius rotates around the circle, what we can see is it's modeling all possible shapes of right triangles, okay? And because the hypotenuse of all these triangles is 1, right? Because every single one of the right triangles from dropping the leg is 1 for the hypotenuse, they can be scaled really easily, right? That's the whole reason why it's called the unit circle, because it's 1 unit in radius. And we do that because it makes it so that it's easy to kind of scale it up and down to match whatever triangles you're working with or whatever sized shape you're working with, right? I have this like really cool page that I wanted to show you guys. Can y'all see this? I liked this a lot because I was looking everywhere for like an animation showing the radius going around the circle to create the triangles. But this one, I can actually do it myself. I was like, this shit's sick. So you guys see here, like as the radius moves around our unit circle, I'm modeling right triangles of every possible angle, which means I'm modeling every possible shape of right triangle. Do you guys see that? So you can see the coordinates here are changing as I move it around. So here is angle 0, and it's at 1, 0, like we saw. At angle, hey, can I get it to 30? This is kind of not super easy to do. You can see it's like 0.5 when it's close to 30, right? And so on. In fact, guys, what you'll notice is that we have so far only been working in the first quadrant, but in reality, the unit circle expands even our ability to work with right triangles beyond the first quadrant. So you can see I can actually work with angles that are bigger than 90. I can work with angles of any size as I go around the unit circle. And I end up getting these coordinates that have negatives, right? So what we end up seeing is that actually, once we start doing sine and cosine of different angles, you can have sine and cosine be equal to a negative value. I could have my coordinates be in the third quadrant. I could have them be in the second quadrant. I could have them be in the fourth quadrant. It's not just the first. I hope that this kind of helps you guys see a little bit of like how the unit circle is creating all these right triangles in every single possible direction, right? So that's what the unit circle is. So now let's look at why does it matter? How does it even connect with what we're doing, right? I think the first day of class, I was showing you guys a lot about kind of what is trigonometry used for in the world, a lot of like, how does it get used in modeling and things like that. And something that we were talking a lot about was called cyclic behavior. Essentially anything in the world that we can observe, which has repetitive behavior. For example, the tides, low tide and high tide. Weather. Weather is cyclic in nature, right? Every year it kind of repeats its same vibe. Sound waves are cyclic in nature. Essentially any wave in the world is cyclic in nature. Radiation waves, gamma waves, radio waves, and all of that. And it all comes into this trigonometric modeling. So this is like a diagram that I created that I thought kind of shows a little bit of like an overview of essentially everything that this whole unit, this whole quarter is even about. So you can see the unit circle, what it's going to do, it's going to enable us to understand and construct trigonometric functions such as sine. Okay, and I want to show you guys why that's the case. So if you guys remember from geometry, the sine of an angle is the opposite over the hypotenuse. That's straight out of SOHCAHTOA. Y'all remember that, SOHCAHTOA? Sine is opposite over hypotenuse, right? Now, when you look at the unit circle though, what do we know about the opposite side and what do we know about the hypotenuse? Anyone have any ideas? What's the hypotenuse in the unit circle and what's the opposite side in the unit circle?
The hypotenuse would be the radius.
The hypotenuse is the radius, and how big is that radius?
It's 1.
It's 1, exactly. The radius is always 1. So the hypotenuse along the unit circle is always 1, right? Does anyone know does anyone have any idea of what the opposite side might be measuring? This one's a little bit tougher. It's measuring the height. So the opposite side is essentially measuring the height of like the vertical height, right? It's measuring the y values, essentially. And it's measuring the height as I go around this circle, right? So in reality, when I put sine into the context of the unit circle, the opposite is height. The hypotenuse is 1. Therefore, sine is literally measuring height over time. So if I ever, for example, had a Ferris wheel, can you imagine how this circle could be turned into a Ferris wheel? And I want to measure the height of a rider on the Ferris wheel over time as it goes around. I could actually use a sine function to model that. And you can see here, the function of sine of x, it looks like this. It does this curve up and curve down. This is literally, if you can visualize it, this curve for the sine function is basically just the unit circle unwrapping as the unit circle goes around, right? And you guys will notice, by the way, I've been doing this the whole time, but I never really pointed it out. But the idea of the angles around the unit circle, they grow as I go counterclockwise. And 0 starts here to the right. So it goes like around and around and around, and it could actually keep going around. My angle can go past 360 degrees. It just goes around and around, right? And you can see as the angle continues, right, as the input of my sine function, which is the angle, as it grows, it goes up until it reaches a maximum, and then it goes down until it reaches a minimum, and then it goes back up and goes back down, right? It's cyclic. you can see that that actually ends up showing up in the graph. Now, trigonometric functions end up being essential toward developing models of any of these cyclic behavior things, such as this sound wave, which I'm showing right here. This is actually a depiction of a sound wave, and it may look kind of, less clean than this perfect sine function, but it actually is just it could be modeled using a composition of sine functions. It's kind of crazy. I actually took a class in college called Physics of Music. And we learned a ton about trigonometry in that class because that's pretty much what it was all about. It was just about modeling modeling sound waves using trigonometric functions. So we are probably not going to quite get to modeling sound waves in our class, but this is saying kind of that's like the future of what does trigonometric modeling unlock, right? Okay. So what we're going to do is in our class for the rest of today is we're going to be working on deriving the unit circle. All right. You'll notice that I've been talking a lot about what the unit circle is. I've been showing you guys all this stuff about it, right? However, we still don't know actually how to make it. We haven't really done that yet. We made the first quadrant, right? We made that whole first quadrant in our mastery assessment. But today, what I want us to do is we're going to take that first quadrant and we're going to expand it to all around the circle. Okay. So at this point in our class, we've done much of the difficult work, right? We've done actually a lot of the difficult work. Getting those first couple coordinates on the first quadrant is the hard part, guys. So now we get to kind of reap the benefit of that and try to construct this unit circle, okay? So you can see here, this is the first quadrant of the unit circle, right? It's got 0 degrees, it's got 30 degrees, 45, 60, 90 degrees, right? Those are the breakups of the angles that we care about. And we're going to look at all the multiples of these angles around the circle, essentially. So when we're looking at the rest of the unit circle, guys, what we're going to be able to do is we're going to be able to derive the remainder of it using this first quadrant in reflection. Y'all remember reflection? Reflection from geometry. You can actually use reflection to understand what the coordinates are around the unit circle. Because what you're going to find, guys, is that these coordinates that we have in the first quadrant are going to just end up repeating themselves because when I have a right triangle, which has a 30-degree angle, to the right of the y-axis versus the left, it still has the same side lengths. It just is going in different. Exactly. You just change the order or make it plus or minus. Exactly. Just as Christine's saying. So some tips I have for you guys when you're doing this, try to solve for all the angles around the circle first. Keep in mind that the whole circle is 360 degrees, right? So would we be making it negative if it was to reflect over the fourth quadrant? Yeah. So imagine, you guys will see it actually once I send it to you guys. So I'm gonna actually, let me copy paste this. So guys, this is our final thing for today. So you can see I've sent y'all a link in the Zoom chat. What that link is going to take you to doing is going to take you to make a copy of, it's going to have you make, all right, hang on, let me just click the link that I sent in the chat. It's going to ask you to, oh my God, it wants me to sign in. It's so annoying. I don't want to have you guys. So it's going to ask you to make a copy, right? And when you hit make a copy, it's going to pull up this. Do you guys see this? So you can see I put this together for y'all. And essentially here is a blank unit circle with the first quadrant filled in. And I have left spaces for you guys to fill in all the other values. So what I want you guys to do is first of all, figure out all the angles around what the angles would be. Notice, by the way, y'all, that these spacings for these angles are the same as the ones over here, right? So for example, what might half of the circle be, y'all? Could someone say in the chat or out loud? What do you think? What's half of a circle? How many degrees is that?
180.
It's 180 degrees, right? So this angle here is 180. Okay. Notice that 1/4 of the circle was 90 degrees, right? So if I want to go another quarter from 180, what's this angle going to be, y'all? What's this angle going to be?
270.
270, right? And you guys can continue using this same idea, right? Notice that from the 90 degrees to this next one, it's the same as from 90 to 60, right? That's a difference of 30 degrees. You guys see what I mean? It's a difference of 30 degrees.
150.
So it's actually, this one wouldn't be 150 because that's 90 plus 60.
So
And notice
120.
exactly like you say, Victoria. This is 120. 150 would be when I add a 60-degree angle to 90, right? Which would be over here. Can you guys visualize how this angle here from 90 to this one is the same as from 0 to 60?
Oh, you times 30.
Yeah. Another way that you can view it, guys, is like, for example, from the x-axis up to the next one was a difference of 30 degrees, right?
So 135.
Yeah. So like, for example, from 180 up 30 degrees would be 150, right? So what I want you guys to do is work on finding all the angles around this unit circle. And then once you have those angles, you should be able to try to figure out the coordinates. What I'd recommend doing, if you don't want to end up having to type, square root 3/2 a billion times and all that, go ahead and copy paste, because I've kind of given away the secret already, but what's going to end up happening is
Wouldn't it just be like the same thing but negative?
exactly, right? We're using reflection here. Oh, I just realized I didn't include ones on the template for the 180 and the 270. So if you guys could add that yourself, that would be nice.
So,
What was that?
so since they're all right angles, we could just use similar triangles to help solve the coordinates.
Exactly. That is what we're doing. So I'm going to go ahead and let y'all try to work on that. So my tips that I had for you guys: find the angles first, and then determine the coordinates of each point on the axes, right? Like the ones on the X and Y axis. And then finally use the special triangles, coordinates, and reflection to figure out the rest of it, right? Looking at our timing for class today, this might end up becoming something where I make it kind of like a small homework for y'all that I want you guys to do. I think what I'll do is I would encourage y'all to try to do it before you watch the asynchronous video for this week. Because in the asynchronous video this week, I'm going to assume that people have already taken some time to try deriving these coordinates and such around the unit circle. But I think that I can't give us enough time in class today, because what I was originally hoping to do was, once people start finishing, we'll have a classmate sharing theirs. So I think what I'll do is, for this week's asynchronous video, I'll start it off by kind of giving you guys the solution to this unit circle thing. That way people can check their own work. But I would like you guys to try it out first before you watch that, okay? And I don't want to keep Christine away from her lunch, So before we go, I've got one last thing. And this is kind of like a little Google form for you guys. I'm going to try to create some set groups for the quarter, kind of similar to how I did in quarter one. I had you guys in groups. Chill, Christine. I had you guys in groups that were kind of consistent throughout the quarter. What I'd like to do is get kind of your guys' preferences down. So this is a totally optional form for y'all to do. Essentially, it's just asking, is there anyone who you think that you'll work well with? Is there anyone who you don't think you will work well with? So when I'm making my group roles, or not even group roles, just when I'm making the groups for breakout rooms in the future, you can do that. Someone asked me, what's the limit? I assume they mean the limit of how many people you can say. I have no limit. Just know that if you say more people, that's kind of nice for me, because it means that it makes it easy. You're like a free agent that I can put into any group that fits. within those things. I'm gonna try my best to put people with groups that they want to be with, because I think that that'll be helpful for us to succeed and work together. Yeah, keep in mind, by the way, guys, that this means that people are going to have to use their OUSD email for Zoom if I want to use these pre-assigned breakout rooms. I assume you guys already are. So yeah, let's see. Min asked, do we submit the slides somewhere when we're done? Yeah, I'm going to make a post on Google Classroom for today's lesson, where I'll include like a link to the slides and a link to the video of the recording of this in case people need it. And I'll ask people to submit their unit circle there. All right. With that in mind, y'all, this is the end of our class. If anyone has any last questions or things that they want to talk about, feel free to stick around, but otherwise, please say your goodbyes before you go. Wait, are we doing the form? That form, yes, it's for you to put preferences. Here, I'll put it. People are saying bye now, so it's spamming the chat. Bye-bye, y'all. Oh, I sent that directly to Christopher. Lol. Here you go, it's Stephanie. There it is. Bye-bye, y'all.
Is it too late to turn in like the work that was due on Sunday?
Which one? The problem set?
Yeah.
The
Or
problem set, no. The mastery assessment, if you didn't do it, then there's I can put together an alternative
okay,
that
yeah.
I was gonna have people doing because part of the idea of the mastery assessments is that if a person gets less than 3 on the mastery assessments, then I want to encourage them to do a retake anyways. So I'll just have you do the retake, Victoria.
Okay, because I only solved for the 45 degree. I think I did that one wrong.
Okay. Christine said, when you get a 2 out of 3 for the mastery, you said to redo it for full credit, but is that only valid till it's due? So this one's kind of an odd mastery assessment that I did. It's a bit different from what I plan to do with the future ones, because the future ones are kind of more like a quiz, whereas this was like sort of like what would be a class activity, but I kind of wanted to make sure people did it. It was something where I did want you to do it before like today, because today I knew bye Mila, because I knew today I was going over it. So I kind of was hoping people would do it before then. I think I said that somewhere, but I'll give, what I'm gonna do is, Christine, everyone who got like 2 out of 3 and hasn't made it the whatever corrections, if there were some corrections that I set for people, then you can do the retake one. And the retake one's going to be pretty similar in vibe. It's just going to be a little bit different.
Will you post it on Google Classroom?
Yeah, I will.
Okay, thank you. Bye.
All right, bye-bye. What's up, Millie?
In Google Classroom, you asked me to change my answer, and I resubmit. And you changed the grade 3 out of 3, but in areas, it's still 2 out of 3.
Oh, interesting. Okay. I was hoping Aries would update with these things because I have it linked. That's saying for me to. Let me turn off my screen share and also the recording.